Okay, thanks, Sean. So genetics is the study of inheritance and variation, and my work is as an animal breeder is trying to improve populations using knowledge of genetics and variation. So, yeah, all good. Okay. So to start off with a little bit of biology, if a population is sustainable and in equilibrium, each individual only needs to replace itself exactly once, right? And you'll have a new population of the same size. But most populations are capable of having individuals that generate many more offspring than they need for replacements. And so that means that there is always selection going on. Only some of the individuals get to be parents. And we might control that selection, or we might not control that selection. It could be artificial or it could be natural. But either way, the selection that occurs will change the next generation due to those natural or artificial processes. So to take you on a sort of a thumbnail sketch of the last few hundred years, the sort of father of animal husbandry is often identified as Robert Bakewell, and this is an old painting that was done of him showing the species that were of interest to him, and he was interested in improving all of those species, and he sort of indicated that what you should do is choose as parents the individuals you like the look of, and then the next generation should be more like the ones that you like the look of. And he did that in a whole range of species. You'd think of the opposite of that would be not using as parents the ones that you don't like the look of because they're aggressive or they have other characteristics that you might not like. And we know when we look at domestication of most of our species over the last 10,000 years or so, we know they've changed a huge amount by natural selection long before Robert Bakewell published and popularised his ideas. So most species have got much, much smaller than they were originally because we seem to like the ones that are smaller than their ancestors. And you only got to look at things like wolves versus dogs to see what's happened. But same is true of cattle and sheep and other things. So we like things that are less aggressive and better fit for purpose. So after Robert Bakewell's ideas, the next sort of concept that came along was, well, we should actually not just think about what we like the look of, but we should actually record it. We should write it down. And so we might weigh the fleece of an animal, we might put an animal on some scales, see how heavy it is, we might write down the characteristics of it. And then we can use that data to decide if this is an individual we would like to use as a parent or not. So what we're really interested in is how good an individual is at producing the next generation of offspring. And here I've shown you a bull, but this could have been a plant or a dog or anything you like. This thing here is just an envelope of DNA, and we might like the look of that bull or not like the look of that bull, but that's not looking at the envelope is not a very good indication of what his DNA is like. And we use a concept called heritability, which tells us the strength of the relationship between what you see on the outside and what the value of that DNA is for that same particular attribute. So when we look at this bull, and I'm not interested in what he looks like, I'm interested in his DNA, the best way for me to visualise his DNA in terms of how fit for purpose he is to generate a whole lot of offspring from him. And if I generate a lot of offspring from him, they'll all be very variable. In fact, 3/4 of the variation of the whole population will be seen in just the offspring of one parent. And if we look at them, we'll see some big positive numbers and some big negative numbers and everything else in between. But many of the reasons that individuals are different are environmental. So a male might be heavier at the same age than a female. One that was born earlier might be a different weight. One whose mother produced more milk might be a different weight. So we have to adjust out all of those non-genetic effects to work out what the deviations in performance would have been if they'd all been born in the same environmental circumstances. And maybe had lots of progeny. This bull was 10 kilos heavier than the offspring of other bulls. So then we might think, since the DNA in here is in pairs, a chromosome coming from mum and one coming from dad, if his offspring are better by 10, then he must be better by 20. The trouble is, that when we see this kind of data, we can't always believe it. And when we don't know if we can trust data we see, we shrink it. So our statistical methods, we shrink it a little bit. So if he had 80 or 100 progeny that averaged about 10 kilos more than another bull, we wouldn't say he was 20 kilos better than average. We'd say he was 16 or 18 kilos better than average because of that phenomenon called shrinkage. So Al Ray was the head of department when I first started in the sheep husbandry department at Massey, and he pioneered the theory and application of genetics to livestock in New Zealand. So Al was the one who started measuring data on sheep farms, adjusting them for the non-genetic effects, and ranking the sires. And he was the first Massey staff member to be honoured with FRS NZ because of that work. And he introduced the use of computers to do this kind of activity long before banks used them to work out what your account balances were. Another very influential person was Henderson, who invented a lot of the statistical methods for separating out those environmental and those genetic effects at the same time. Prior to that, we adjusted for the environmental effects, then we looked at the family information, and he worked out how to do it together. And many of us, like myself, were lucky enough to go to Cornell and learn things from him. He was a National Academy of Science holder, and interestingly, he invented this methodology in his PhD, but he couldn't prove it, and it was proven on one sabbatical he took on his life, which was here in Wellington in New Zealand. And then about the same time, there was this other idea about how good a parent was, which wasn't directly looking at the offspring, but it was the idea that on these pairs of chromosomes we had alleles that could vary, and if we had a number of positions that affected the performance and we had positive and negative values there, we could sum them all up and we could get the merit of the individual from looking at its DNA. So two completely different concepts of a breeding value, one from offspring and one from looking at the average effects of these infinite number of genes, idea that Fisher, a very famous statistician, came up with. The trouble was we'd have to know what these numbers were. If we knew what these numbers were, we could add them up and get the answer. And that's where this guy Pearson, who did a lot of work inventing regression, looking at the relationship between the heights of parents and the heights of their offspring, and he came up with the idea that we could do this by regression. So if we have different sires that have different progeny performance, the reason they have different progeny performance is that some have more copies of the favourable allele and some have less. And if we choose a bull with a good breeding value, better progeny, on average he's got more better genes. So we just take that idea of Pearson and we do a regression of the breeding value on the number of copies of a particular allele that we can see using some molecular technique. And the slope of that line tells us how influential that locus is on performance. And that's exactly what the company 23andMe did to predict performance in humans. So this is my merit for coronary heart disease. Each little bar here represents one locus, and a red bar means I've got an unfavourable allele. A green bar means I've got a less favourable allele. If you sum them all out, you can work out the risk of coronary heart disease using exactly the same technology that we use for predicting animal merit. Come on. Okay, so then the next big breakthrough that came along was this trio, Tao Newis, Ben Hayes and Mike Goddard, who invented the idea that we could simultaneously do this regression that Pearson was doing at every locus in the genome all at once. And rather than just using the significant ones, like 23andMe did, we can use all of them at once to get better predictions. So my role in all of this has been a lot of things to do with the theoretical aspects of prediction, but also to do with the applied aspects of prediction. In the pre-genomics era, I was applying these methodologies that people like Henderson invented to ranking the dairy cattle in New Zealand. In the post-genomics era, I was involved in using various Bayesian regression models to make the assumption that when we've got millions of these SNPs in the genome, most of them probably have no effect. So when we're trying to do the estimates of regression, any particular locus might have an effect that's zero or might have an effect that's real, and it's what we call a mixture distribution. So fitting a mixture distribution to that kind of analysis. And then more recently, I've been involved in a lot of implementation and teaching of these technologies using R and then using Julia, using open source software, and then through spin-off companies developing command line Unix tools, particularly using graphics processors to deal with these kind of evaluations for real organisations all around the world that are interested in improving their populations. Thanks.
For that nice tour of your field. Very interesting. Do we have any questions?
So I worked on a project for a while that was related to AI, and I mean the artificial insemination part, not the artificial intelligence version. And I observed something really interesting between the period of about 2012 to maybe 2018, where in 2012, if I'm talking to people working in a company like Select Sires or CRD, they were saying, well, you know, we've got these genetic tools, but we're not really sure if they really link up to the phenotypes we care about. By 2018, they almost weren't looking at phenotypes anymore, they were looking at the genetics directly.
Right. Yeah.
So my first question is, that's a really fast transformation in the decision-making in a multi-billion-dollar industry. Do you have any insight into that? And my second question is it done, or is there something coming along after that? What's the next thing?
Right. Yeah, so I mean, it's, as I said at the outset, the best way to work out how good an individual is to generate a lot of offspring. And that's what companies did in the past, whether we're talking about plant breeding companies or animal breeding companies. They tested offspring in lots of environments, and they knew and they could trust that data said this individual was better than average or worse than average. This sort of idea of summing up all those effects of those alleles meant that you had to estimate them. And how well could those effects be estimated? Were they really additive? Were they epistatic? There's a lot of complexity, so there was a lot of distrust, if you like. But because many of those companies had kept the DNA on their old progeny tested animals, they could genotype them and retrospectively apply these analyses to historical data. So as the cost of genotyping came down, people were able to genotype maybe 1 million bulls and work out, based on those historical animals, which alleles are trustworthy and which ones aren't. And that's really what's led to the development of the confidence. Like anything, people don't really believe it until they can really see that it works. In, say, the human area, we're just still seeing the early stages of this being developed, where people don't really know if they can trust those predictions of my likelihood of getting heart disease or diabetes, and they don't always understand that, you know, there's also environmental aspects that can modify things, and then there's just chance. They don't understand variation. That just because you're more likely to have a particular outcome doesn't mean you will have that outcome. What's next? Well, now that we know what some of these genes do, we can sort of mix and match individuals to generate combinations we maybe wouldn't have seen elsewhere, or we could gene edit. So those are some of the things, but there's still enormous opportunity for just old-fashioned selection, ranking the individuals and choosing the ones that will move the population in the direction we want it to be in the next generation.
Just a question about unintended consequences. You know, one of the results of this process is sort of a loss of diversity, genetic diversity potentially, in a species. Has that you know, have there been that kind of that effect where we've sort of lost wild type genes that later, you know, we might have wanted to keep around? Is that something that's
there's small elements of that, but it's not nearly as bad as most people think. So if you eat pork or you eat chicken or you eat eggs, those come from multi-line crosses. So any egg you eat is actually from a hen that's a 4-way cross. So she's a cross of 4 completely different lines. So those individual lines are inbred, but the rooster will be a crossbred and the hen will be a crossbred, so the offspring is a 4-way cross. So within a line there's loss of diversity, but across lines there's not necessarily.
That's maintained, and that's a deliberate.
It's more of a problem in things like dairy cattle and beef cattle, where people for some reason get so excited about Angus or Holstein, instead of having a balanced representation. And we have the same problem in plants where there's an overemphasis on maize and soybean because they're incredibly productive and not nearly enough emphasis on all of the other crops that could be useful.
Okay.
Good one. Is there anything in there for selecting or creating All Blacks?
Yeah, absolutely. We can do that too.
All right, well, let's thank you.